Now, what is going on here and why is this happening? Think about the beginning of the experiment when water was boiled in the can. Since the can did not change shape as the water was boiled, we can deduce that the pressure outside the can was equal to the pressure inside the can. Therefore, P outside equals P inside. The pressure outside the can was simply just the atmospheric pressure, but it would be wrong to say that the pressure inside the can was mostly exerted by water and air, assuming pressure from other molecules were so small they were negligible. This is because we have to remember that when water was boiling inside the can, water vapor gas formed, and this gas was displacing the air that was originally inside. As a result, the pressure inside the can was actually exerted mostly by the water and water vapor, where the initial pressure inside is equal to the pressure of the water plus the pressure of the water vapor. So if we combine these equations together with the previous one, we get the atmospheric pressure is equal to the pressure of the water plus the pressure of the water vapor. The equation we have right now defines the pressure balance at the start when the can was heated. When the can was flipped over and put in cold water, the water vapor near the can opening comes in contact with the cold water, causing the water vapor to condense, taking up less space in the can. This decrease in volume lowered the overall density inside the can. And given that pressure is equal to rho gh, density is directly proportional to pressure, and so when density decreases, the pressure decreases as well. Knowing that the overall pressure inside the can decreased, it means that P inside 2 will be less than P inside 1. And if we plug our equations back together, we would find that after cooling the can with cold water, we get the following. P water 2 plus P water vapor 2 would be less than the atmospheric pressure. And this means that the pressure inside the can will be less than the pressure outside. This imbalance in pressure caused the can to be imploded/crushed. From the reasoning above, we can finalize that the can imploded because of the sudden change in pressure inside and outside of the can caused by a change in temperature from hot to cold. After we did some research on this experiment, we found that the main cause in pressure change was due to the rapid condensation of water vapor. However, we were curious about what was the root cause of the condensation. Looking at Mohazabi's paper, The Physics of the Imploding Can Experiment, 2010, we also found that the rapid implosion was due to the rapid condensation of water vapor when it comes in contact with the cold water near the can opening, as opposed to the condensation on the interior of the can. Mohazabi demonstrated this by setting up two variations of the original experiment. In the first experiment, before the can was exposed to cold water, the can opening was plugged. This change caused the can to implode significantly slower and more gradual than before. In the second experiment, the can was covered with silicone caulk which acted as a thermal insulator, but the can opening was not plugged. Despite the insulator, the can still imploded rapidly. Mohazabi's further investigation shows that the rapid condensation near the can opening was what caused the pressure change to occur so quickly, resulting in a fast can explosion.